Hello. In this video, we are going to discuss dead load. The learning objectives for this short lecture are as follows. To 1, understand the process for calculating dead load, and 2, analyze if we should use the computed dead load or not. For some background, in the Tier 1 checks, which is currently taught in BP211, we take the dead load to be a conservative 1.0 kilonewtons per meter squared, and with a deck width of 1.04, this becomes 1.04 kilonewtons per meter, which you should already know, and as you can see in this graphic below. Tier 2 calculations will require you to actually calculate the dead load using weight of material of the bridge. Correct. That is the deck, crossbeams, suspenders, fencing, and cable. However, we don't exactly start with a fully designed bridge. So in the design phase, we're still going to use the conservative 1.04 kilonewtons per meter to start. And when we have calculated the dead load, we can go back and check that this is not more than our 1.04 kilonewtons per meter. Ultimately, it can then be used to sharpen the pencil on the design even further. If we go back and the calculated dead load is less than our conservative assumed dead load, we could potentially use that. If it is more, we should assume that value. Now first, let us work our way top down and take a look at the deck and crossbeams. The decking is a continuous layer across the bridge span, so in order to calculate its line weight, we have to find its thickness times width times density to get the weight of the deck. Now that would be the full width of the deck times the thickness of the deck times the density of timber to give us for the crossbeams, they're oriented differently and spaced at 1 meter apart. Depending if they have a nailer or not, which depends on the walkway detail, we'll take the volume of a full nailer and the volume of a full crossbeam and then divide by the spacing to get its line weight across the bridge. These dimensions depend on the walkway detail. But ultimately, we will have that area of the nailer here, an area of the crossbeam here, multiplied by the various thicknesses to get volume. So our equation will look like our nailer times the density of the nailer, which is going to be timber, plus volume of our crossbeam times the density of the crossbeam, which could be timber or steel, all divided by that 1 meter spacing S. Suspenders and fencing are similar. For the suspenders, we'll take the length of the suspender, remembering to use its full length, not bend length, and multiply it by the cross-sectional area of the bar to get volume. This will be multiplied by the density of steel and multiplied by 2 for each side, then divided by the spacing. Fencing has a unit weight reported in square meters, so we only need to multiply by the height and then multiply by 2 to get its line weight. So for the suspenders, we'll have our volume of suspender is just going to be that length times area of the suspender, and that's going to give us our W suspender is going to be our volume of suspender times density of steel times 2 divided by S, which is our spacing, and our volume of, or our weight of our fence is just going to be 2 sides times the height of the fence times the given value for the density of the fence, which will be in the notes below, which is actually going to be in kilograms per meter squared. That's going to give us our weight of the fence. And finally, the simplest material is cable. So also in the notes below, using the provided table of weights, we only have to multiply the number of cables by the line weight to get the total cable weight. We'll then sum all of these factors to get our dead load. So first, our double cable is going to be our number of cables times, I'll just put the density symbol, but that's going to be in per meter. And remember unit analysis on all of these things. So finally, our dead load is going to be our deck, so our cross beams and nailers, plus our suspenders, plus our fence, plus our cable, and we'll compare this with 1.04 kilonewtons per meter, and we'll see if it's greater or less than.